Hey guys, welcome back to my garage. In this video, we're gonna go over the choosing of the components from Clearpath for this machine. I spoke extensively with Clearpath about the project, and I gave them some information. I asked questions, the same questions you guys might be asking them, and I want to go over that with you. We'll take a couple close-ups of the motors and the couplers on this machine, and kind of go over everything, and then we'll do an unboxing. First of all, I'll be using the Centroid Acorn. It has 4 axes of step and direction control, and it has 8 inputs, 8 outputs, and it has a true spindle encoder input. So it uses a line driver differential encoder. 1,000 lines is recommended. There's no need to go any higher than that. When you're choosing an encoder, I like to use the ones from automationdirect.com, or a good quality encoder. I think I'm going to use a Tamagawa on this one, because it's what I've got on hand. You probably want to try and stay away from the cheap encoders, because they may not last, and a lot of them are not designed to have a pulley attached directly to them and then being driven from the spindle. The bearings just won't handle it. The ones from automationdirect.com, you'll be wanting to look at a medium duty or a heavy duty encoder, and you'll also want to watch the max RPM that the encoder is rated for. One of the reasons I like Centroid is that company's been around for over 30 years, and they specialize in CNC motion control. They build the hardware, and they also do the software for their motion controllers, so you don't have to worry about integrating the hardware with the CNC software that you're using. So that's a huge plus. They've got support on their website, user support. It's peer-based. Acorn is a DIY solution, do-it-yourself. So as far as support, they have a support forum for users, and users help each other out. Centroid does have a presence there, so when their technicians have time, they jump on there and try and answer any questions that you might have. The forum has grown by leaps and bounds. There's a number of super users there helping other users out. I try and visit it at least once a day to just check in on things. So it's a great resource, and that is the #1 source for support for Centroid Acorn. A little bit about Teknic. Teknic's been around for over 30 years, specializing in servo motors and servo systems, so they're very well versed in what they do. They have a great team of engineers there that designed the Clearpath SD series of motors. We'll be using SDSK on this one, which is the step and direction stepper killer is what they call it. It has 2 to 3 times the power of a similar sized regular open loop stepper. In speaking with the applications engineer, I bought the whole package. I bought their cables, which were reasonably priced. And we'll go over that when we do the unboxing. So it'll plug in there. And then I'm going to try the C86 ACCP from CNC4PC.com. So CNC for PC designed a board that plugs into the headers. You loosen the screws on the headers, and the board plugs into it with pins. You tighten it down, and then the other end of the Clearpath SDSK, the cable, will plug directly into that. I'm hoping that it turns into a fully plug-and-play solution. Just plug cables into motors, plug into the C86 ACCP interface board, and plug the power cable to the motor and the power cable into the power hub that I got from Clearpath. I got Clearpath's power supply. I believe it's the IPC5. I discussed that with the applications engineer, and I discussed the application, and I told them there's going to be 4 motors on this thing. We sized the motors based on the steppers that were on this thing. The motors that I have on this machine had labels, so I was able to look up the spec sheets for all these stepper motors, and I sent that to Teknic. I sent him the ball screw pitch on this machine, which is about 5 turns per inch. It is friction weight, it's not linear guides. And let's see what else. These motors are coupled at 1-to-1 to each axis. There is no belt reduction, so that was important. And that's the other neat thing is you're not only paying for the motor, the product. So if you need help, they're willing to help guide you in selecting the right motors for your application. Some of the things that they're going to ask you and you need to have on hand before you call them. Get your current stepper motor specifications ready. Hopefully your motors are labeled where you can try and find the cut sheets on your motors. Give a description of the machine, including its travels. Does it have dovetail or boxways, which is kind of friction slides, or does it have linear guides, which are ball bearing trucks that ride on precision linear rails? There's much less friction on those than there is on a machine like this with the dovetail ways. Do you have a lead screw? Do you have a ball screw? And what's the pitch of those screws? Are your motors direct coupled to the screw? Or, as I mentioned previously, do they have a belt reduction? And if so, what's that belt reduction? The stepper motors, what size is it? This machine has NEMA 34 on the X, Y, and Z, and it has a little NEMA 23 on that fourth axis. So you'll need to measure your motors, measure your flanges, and then jump online and you can find out what motors you have. Whether they're NEMA 23 or NEMA 34s or 42s or 17s or whatever. And incidentally, NEMA, if it's technically, it's supposed to be the measurement of the flange of the motor determines the NEMA size. In other words, a NEMA 34 would have a 3.4-inch flange size. Again, the shaft size, determine the shaft diameter of your motor if you don't want to deal with changing couplings. And for the router guys or a large format machine, do you have a master-slave system where a lot of those gantry machines actually have two motors that drive the gantry front and back because they're so wide you can't just put one screw or one drive mechanism up the middle. Usually they have screws or gear racks on either side, so that would be another situation that you want to convey to Teknic. And then you want to discuss what kind of rapids do you expect out of the machine. Along with what type it is. Is it a mill? Is it a lathe? Is it a router? Is it plasma? Is it water jet? Something like that. You want to give all that information to Teknic. This is a small format mill. It doesn't need to move at 500, 600, 800 inches a minute. The travels are so small. I'll probably limit this to about 100 inches a minute, which is plenty fine for this. We might test it a little bit higher than that. I think what's more important here is the cut, what the work that the machine's actually doing. That's what we care the most about. There's no tool changer on this machine, so I don't think we need to worry about running this thing at 500 inches a minute. And things happen really fast when the machine's moving, and to smack that e-stop button on a machine that's moving that fast, I don't know, something like this, I think it's going to hit a hard stop or something's going to happen before you're able to catch it. The Clearpaths have fault mechanisms, as do most servo drives. If they hit a hard stop, they'll know that and they'll fault out. Teknic also has a really good video, which is a general overview of all the components of their system, from motors to cables to the power supplies to the power hub. And you need a standard. It's basically a USB. I think it's a USB programming cable, which is pretty standard. I just bought it from them so that I had the right one. We'll do the unboxing here, and you'll get the overview here as well. I haven't opened the packages yet, and you'll see it when I see it. I'll also put a link in the description for Clearpath's accessories guide. They have a link on their website. Also, Teknic has wonderful tutorials on YouTube. I've been watching them, checking them out, that go over the SD series motors. They also go over their MSP software for setting up the motors. So while I'll go over that, I'm going to get into tremendous detail with it because they've done a really good job of doing it, and being this is my first crack at setting up Clearpath, they'll probably do a better job at explaining it than I would. Some of the other interesting things when I'm talking to the rep, So Clearpath, if you haven't seen it, and we'll see it when we do the unboxing, is the drive is built on the back of the motor. So you don't have a separate drive and a separate motor. They're all together, so that simplifies the wiring from the drive to the motor, so you don't have to worry about that. It makes for less complex wiring and a smaller cabinet footprint. I'll post a picture of the current cabinet on this machine, which has 4 stepper drives in it, and you'll see how it's very compact, it's very tight in there. In fact, the Acorn that I used, I had to put the output board over the Acorn because there wasn't enough space in the cabinet to lay that relay board alongside the Acorn. So all those 4 drives are going away because those are all built onto Clearpath motors. So that in itself, the simplification of you don't have to wire it and it's all in one unit, that simplifies things, makes for a smaller cabinet. Also, they tell me that they have designed and engineered the Clearpath motors and drive system to be very, very noise immune. So it's less susceptible to electromagnetic interference. In fact, their cables, I'm told, aren't even shielded. So they've done the engineering to negate the need for special cables, which helps keep the cost down. The cables come in 2 lengths at Clearpath. I think I've got the 10-footers, the smaller ones, and then they have a 55-footer. So I'll end up coiling the excess cable in the bottom of the cabinet. But the point being is one end of the cable has a molded mini-fit junior connector on it that plugs into the motor, and that's where you want the molded cable, the molded connector to plug into. And the other end is just a mini-fit junior. It's not the molded type, but it will plug, in my case, it'll plug into the power hub, and it'll plug into the C86 ACCP board from CNC for PC. So it's just plug in. I don't have to do anything. I don't have to cut. I don't have to strip wires or anything like that. Their reasoning for the 55-foot cables, if you have a large format machine, you can cut the cable in half and you've got the connectors on both ends already, and then you will have to terminate those wires on the other end. They told me Clearpath has a 3-year warranty on their motors. They have a 90-day exchange policy. Let's say you guessed wrong or you weren't satisfied with the performance of a motor and you want to exchange it for a different motor. They will take that within 90 days. So they figure 90 days is more than enough for you to get your machine up and running and decide whether or not the motor's correct. But take the time, give them as much detail and as much as you know about your current setup. So that they can give you an accurate suggestion for a motor so that you only do it once. In my case, it's going to be tough to get the y-axis motor out because the y-axis is at the base of the column and behind the cabinet. So that would be a real bear to take that thing back out and have to pull the cabinet back off this machine. The only way to do that is take the back panel out, so it's almost like starting all over. So you want to kind of nail that down as best you can. But it's good to know that if a mistake's made, Clearpath's going to stand behind it. Oh, and we talked about the MSP software. It has auto-tuning features in it. They've engineered the software so that when you get the motors, they're tuned for no load, so you can bench test it. You can get the motors turning on your bench. You don't want to hook the motors up to the machine without doing the bench test, and that's what we're going to do. You want to do a bench test first, establish that all your motors are running, do them one at a time, get them all running, then mount it to the machine, and then once they're mounted to the machine, then you can use their MSP software to tune them. So their tuning software eliminates some of what I call the black magic of tuning servos. So it'll get you really close. If there's some fine tweaking to be done, that Teknic would be able to step in and help you make some minor tweaks. But it's nice to know that the auto tuning's there for those of us that are challenged when it comes to tuning servos. Let's go over open loop versus closed loop for some folks that may not know the difference. Okay guys, I'm going to go over 3 different types of CNC control systems. The first one is an open loop CNC control, and that's what Acorn is. It's open loop control. In other words, it does not receive any kind of feedback from the motor, because the motor in this case is a stepper motor and it doesn't have an encoder. So we have Centroid Acorn, we've got the stepper drive, and we have a stepper motor. And like I mentioned, the stepper motor doesn't have an encoder on the back of it. So there's a pulse stream and a direction signal that goes to the stepper drive, and the stepper drive sends electrical signals to the motor to turn it. The control doesn't know if that motor turned to its correct position, and the drive doesn't know whether or not it turned to its correct position. In this type of a system, it's very critical that you choose the drive and the motor given the application. Also, with an open loop system, if you stall the motor, the stepper motor, the control won't know, the drive won't know if it's stalled. You can lose steps, and losing steps is by ever so often stalling that motor just a little bit. And if that happens, let's say you're cutting a circular pocket in a part and you stall that motor in that pocket, you might see artifacts in your part. The motor and the control can continue to run, and you won't notice it until after it might be too late, that there's like a stair stepping, or your circle is no longer round, it's offset, or it has artifacts in it. Some stepper drives have an alarm system that would go to Acorn's drive fault input. Many of them do not. Open loop, there's no feedback, no encoder on the stepper motor. There's no way to get that information back to the drive or get that information to Acorn. In a hybrid closed loop CNC control system, Acorn is still an open loop control. It does not receive any feedback from the encoder on the motor. Again, Acorn will send out a pulse stream and a direction signal to the drive. The drive will interpret that and send an electrical signal to the motor to rotate that motor. The motor in this case has an encoder on it, and the encoder sends feedback back to the drive, and the drive is monitoring that feedback to make sure the motor's in position. If the motor's lagging a little bit, that drive will push that motor a little bit harder to try and get it to where it needs to be or end up. So this is a closed loop here, all right? So the drive tells the motor to turn, the encoder on the motor is telling the drive, did it get to where it needed to be? If in this case you stall that motor, and it's difficult to stall a motor like this, if it stalls, the drive will finally give up and fault and send a fault signal to the Centroid Acorn. So there's a chance that you can salvage the part in that case. So the drive is closing the loop. You see the loop here? The drive is closing this loop. All right? In a true closed CNC control system, in this case, I've used Oak as an example. Oak will send the signals to the drive, and the drive in turn will turn the motor just like this example. Will turn that motor, and the encoder on the motor will feed back to the drive, and the drive will make sure it's in position. The same encoder signals that come into the drive are also fed to the motion controller, so the motion controller knows where that machine is at any given time. This is a true closed-loop CNC control system. All right. Now getting back to this hybrid closed-loop CNC control, it's a hybrid because it's a mix of both of these. It's an Acorn step and direction, and the motor has an encoder on it to give feedback to the drive, and the drive is ensuring that the motor is in position. If it's not, we'll get a fault. In this case, the Clearpath SDSK right here has its drive and encoder built onto it. So what you see here, the motor, the encoder, and the drive is all built onto the SDSK motor, which is really nice. And then there's the two connectors. We got one for power and then one for the data signals. This is a closed loop system. Just like we said here, it's closed loop. The drive is ensuring that the motor is in position. If it's not, the drive will fault, and it'll tell Acorn via its drive fault input that there's a problem, and Acorn will stop immediately until you can take care of the problem. All right, so that's an overview of open loop CNC control, no encoder. That's the easiest way to think about it. Here's a stepper motor. There's no encoder on the back of it. So it just turns based on the signals, the electrical signals from the drive, and based on the pulse stream sent to the drive, but it's up to you to make sure this is right. Of course, it's up to you on both of these to make sure that you're choosing the right motors, the right drives, and so forth. But usually, in this case, the drive is already chosen for you. It's already been selected, it's already been sized for this motor. All right? Typically in this true closed loop system, the motor and the drive are matched up together. If you buy a 750 watt system, you get the motor and the drive. All right, so I hope that helps give you a little bit of a 10,000 foot overview on open loop CNC control, hybrid closed loop CNC control, not to be confused with the Clearpath motor, which it's in and of itself is closed loop. Here's the loop, it's closed. And then a true closed loop CNC control system where the motion controller also gets feedback from the encoder to know the position of the motor. One other thing to note, it's up to you to make sure that your machine is mechanically sound. Your ball screws, your ball nuts, your thrust bearings, your drive system is tight, mechanically tight. The machine has to be mechanically sound to get good results. So because all these encoders are on the end of the motors, they're just being monitored. The motor's being monitored. If it's told to turn 2 revolutions, did it turn 2 revolutions? But you have so much slop in your drive system that you went over or you went under because of the lash or the slop in your system, you're not going to get good results. That's number one. So your machine has to be mechanically sound. The other thing I always recommend to people that want to get into CNC is I recommend that they find a purpose-built CNC machine to begin with. Otherwise, you're taking out Acme lead screws and you're trying to fit it with ball screws and you're putting ball nuts, you're making mounts and all that stuff. And you can't cut corners. You can't buy the cheapest ball screw that's out there and expect it to be of any decent quality. A cheap ball screw might be better than a worn out Acme screw, but if you have lash, you have lash. You have mechanical lash. Yes, the Centroid software has lash compensation, but you can't make up for mechanical lash, and it'll show up in circular parts. You know, they won't be perfectly round. They'll be off. The mechanical accuracy, the mechanical stiffness of the machine is up to the builder, it's up to you. Now, even a CNC machine like this, if it's really worn and old, it might need some work, but it's easier to pull out a ball screw and replace a ball screw where one was before than it is to make mounts, select ball screws, turn and grind the ends of the screw to fit your bearings and your nut and your coupler and all that business. So, anyway, try and start with a purpose-built CNC machine. Yes, there are people now that are making kits like for the Grizzly G0704 and the Precision Matthews machines. They're making kits. Check with them. Ask them, what's the accuracy of your ball screws? What's the accuracy of the system? Is it completely bolt-on? Will I have to modify or grind? Going that route is better than going it completely alone, having to engineer the whole thing yourself. They have usually already done all that engineering work for you. They've already designed the mounts. They've already picked the ball screws out, all that sort of stuff. So that's the second best way to go. You know, find somebody that has a kit form. Just ask them, what's the lash? What should I expect for accuracy out of your ball screw and your thrust bearing? That's another thing that you need to watch for, is the thrust bearing, because you're always got force going at it or from it. So that thrust bearing has to be tight. It has to be a good angular contact bearing or bearings in order to minimize the backlash. And when we do this machine, we'll go over how to check for lash on the machine. Since this machine's already been running, I know that it's got less than 1 thou of backlash in the 3-axis. It's actually not terribly bad for what it is. Oh, and the other thing is, be realistic about what you expect out of a machine as far as accuracy goes. This is a benchtop machine. It's purpose-built. I think it's pretty well engineered for what it is. But I think I think it's unreasonable to expect tenths accuracy out of a machine like this. You know, I think for hobby use, I think, 1 thou, 2 thou, 3 thou is probably good enough for the type of work that we do. Once you learn the machine, then you know what you can do to accommodate or work with what you've got to make good parts. Okay, there's no substitution for rigidity. That's the other thing. This is nothing like a machining center. So, but it is pretty heavy. It's got heavy castings. It's cast iron, so it's pretty rigid for what it is. So I'm just saying, don't over expect out of something like this, you know. So that's the other thing. The other thing that you have to also keep in mind and always take into consideration, when you wire the cabinet, you have to use good wiring practice. You can't have a rat's nest. You can't have wires going all over the place because they act as antennas. If you have a variable frequency drive, they emit an enormous amount of noise. And you pick that up, and between the Acorn board and the drive, that wire, if you disturb that pulse train or you add or take away, you're going to have problems. The counts that left Acorn are not going to be the counts that make it to the drive, and the drive is just going to interpret what counts it got. So it's going to turn that motor based on what it received. And because Acorn is an open loop controller, it doesn't know where the table's at. I sent out the stream of pulses that you told me to send out based on the movement you called the control to move. So you have to keep your wiring clean. You have to eliminate ground loops. And all I could say is if you have shielded cable, ground one end of the drain wire, that shield, to one ground common point. I take it as far as going to where the service ground enters the cabinet. So all those drain wires go to one point. The other thing I can't overemphasize enough, and I say this from experience, it's bitten me several times, is buy the VFD cable from automationdirect.com. It is a bulky cable. It's the 4 conductors for 3-phase plus a ground, and then that has a braided shield over it. It's a really heavy duty cable, and it needs to be installed properly from motor to the VFD, and we'll go over that on this machine. Spend the money and buy the good cable. Anything that's exposed, anything that has no shielding, it's a crapshoot whether or not you're going to have trouble with EMI. And when I'm on the Centroid forums, I see this time and time again when I look at the user logs. And by the way, in CNC 12, if you do F7 utilities, F9 logs, and then F1 errors, you can see your log file, the error log, and you'll see these PC sends, MPU resends, and all that. That's noise that is also interfering with the communication between the CNC PC and Acorn, and that has to be resolved. You've got to clean that up. All that can be the result of ground loops. You're not grounding things properly or in one spot. You have wires all over the place. You use the wrong kind of wire, that sort of thing. And it's really easy to blame the controller or the drives or something like that, when in fact it's usually the result of not wiring something properly. So I can't overemphasize that enough, and I've been there. I've had my share of that sort of thing, and so I try and wire things up correctly. So keep it neat, keep it clean. If you can keep power, you know, anything above low voltage on one side of the cabinet and low voltage on the other side, so high on one side, VFD on one side, low voltage signal wires on the other side, that would be best. If they have to cross, try and make them cross at 90-degree angles. In other words, if you have AC crossing DC, have them cross at right angles, not parallel to each other. Okay, just giving you some tips there. Another thing, I'm going to back up just a little bit because this little coupler reminded me of that. When it comes to mechanics of your machine, how your motor couples to the ball screw or the drive system on your machine, try and stay away from these little things, because they're a spiral cut thing, and what ends up happening, if you over torque these, or the motor's over torquing that, you're unwinding it and you're winding it, you're unwinding it and you're winding it. So this can introduce lash into your system. You want a rigid coupler. Lovejoy makes them. The Oldham couplers, it's another one to look up, they make them. You want to have a flexible coupler between your motor and the screw. If you're, in this case, like I said, I'm direct drive. But I'm not using couplers like this. This might be fine for a very small, very low torque application, but not for something like this. Stay away from these. They're cheap, yeah, $5 to $10, but they're gonna bite you in the butt. You're gonna wonder why you don't have the accuracy you're expecting out of your machine. I'm gonna bring you up to these couplers. Let's take a quick look at them. Okay, here you see one type of coupler, and it clamps. It clamps to the ball screw and it clamps to the motor here, and then it has plates that are attached to a center section and then to each side of these clamps, and it allows it to have some flex, but it's still direct drive, so it doesn't unwind or wind like that coil type coupler I showed you a minute ago. This is a really good coupler, but this helps your mechanics on your machine. Okay, I also mentioned that I'm going to try and put an encoder on the motor just as an experiment, because it just happened that the motor on this machine is belt driving the spindle with a timing belt, and they're belted together at 1:1. So as long as I keep tension on that belt, I should be able to put an encoder on the end of the motor. I'm currently putting new bearings in the motor, and then I'll machine the end of the shaft, because it has no fan on the end of it. It has a muffin fan on top to provide forced air cooling on that motor, which is a good thing. It's a way you want to go on a motor that's VFD controlled and you're running at lower speeds, because the fans that they put on them aren't necessarily going to do the job of keeping that motor cool. So an auxiliary fan blowing down will help. I initially thought I would make the shroud taller, but I don't need to. The fan currently is on the inside. I'm going to take the fan and put it on the outside, and I'm hoping that I still have room for the encoder on top of that motor. I'll be using, I believe it's a 1000 line encoder there. Let's see if we can get this thing to rigid tap accurately, and I'll be testing that in machinable wax. Let's see, I think that's it. Let's go over to the table and let's unbox and see how it goes. Okay, I hope this turns out well. Things are kind of rigged up with my camera overhead and it's kind of shaky. So as I didn't explain, I'll be reusing the Centroid Acorn that's in the machine now. So there won't be any unboxing of that. Centroid's done an unboxing. We will do a bench test with the Acorn. Let's go ahead and open up these boxes and see what we've got. There's a packing list here. Get rid of paper. All right, here's the 4 cables. This carries a step and direction signals from Acorn to the SDSK. Let's open one up and take a look at it really quick. Okay, there's that molded connector we were talking about. This will plug into the SDSK Clearpath motor, and then here's the other end. That'll go into the C86 ACCP from CNC4PC.com. It looks like here we've got so we've got 4 motor cables, motor power cables. Let's see, 1, 2, 3. There's the 4th one. Let's pop one of these open real quick. Okay, same thing. Here's there's the molded end that will go into the Clearpath SDSK, and here's the connector that plugs into the power distribution board. I think this is what they call the Saber connector. All right, so we got 4 of those. This is the PC Saber 72. I believe this goes from the power supply to the power distribution board. So those are our cables. And then here's just a basic USB cable. This is what's going to be used to communicate from the PC to the motors, to the drives on the motors. Looks like 120, so I guess this is about 10-foot cable. That's kind of nice. You don't have to get right up to that motor when you're tuning or setting them up. So I believe I ordered 2 of those. CPM cable M2P2P120. Guess we can look at the packing list here. PC Saber 72, that is the DC power cable IPC to Power 4 hub. So this goes, like I thought before, this goes from the IPC power supply to the Power 4 hub. And this one, the CPM cable M2P2P120, that's the 24 volt. I opted, we'll talk about that power hub in a second, but one of the features is if motor power is removed, if you put a power supply on that hub, it will keep the logic or the drives powered up. The motors don't lose position. It keeps that encoder powered up. So that's what this is. This will go to the 24 volt power supply. So let's see, I ordered another USB cable just to have 2 of them. So that's the second USB cable. Let's see what's left in here. Okay. All right, Power IO 24 volt DC. Okay, this is that 24 volt DC power supply. So using this will keep the logic up on the drives while the motor power is turned off. So that's what that is. I went ahead and ordered it because it's part of the kit. I'm not a fan of these switching power supplies just because of the way they need to be mounted. I like DIN rail power supplies, so I may be swapping this out for a 24 volt DIN rail mounted power supply. I've gotten in the habit of using DIN rail mounted power supplies in terminal blocks. Okay, here's the Power 4 hub. And there it is. And then these will plug into the motors, so they plug right in there. And then the Saber, PC Saber 72 will plug from here to the power supply. So this board will distribute the power to 4 motors. So we'll leave that in the anti-static box for now. Oh, and then there's and then here's the power for 24 volt DC that keeps the logic up on the motors in case the motor power is removed, and that's what this cable's for. So this plugs in here, and then it goes to the 24 volt power supply. So that's kind of cool. I'm interested to see how this works out. Okay, so that's cables, the 24 volt power supply, and the Power 4 hub. That's what this was here. Okay, so this is probably our motors and our power supply. Yeah, here's our packing list. So yeah, so we have 2. In my case, like I said, we have 3 different motors. For X and Y, I'm using a CPM-SDSK-3411S-RLN. And then on my 4th axis, I'm using a CPM-SDSK-2321S-RQN. And then on my Z-axis, I'm using a CPM-SDSK-3432RLN. So I went with the RLN, which has the 800 encoder counts per revolution versus the ELN 6400 counts, because in my case with the pitch of the ball screw, the 800 count will give me 2.5 tenths of a thousandths per encoder count. So that resolution is just fine for my machine. If that had 2-to-1 reduction, then that would be cut in half. So it'd be 1.25 tenths of a thousandths of an inch. So anyway, we determined that 800 encoder counts would be plenty fine for that machine. So don't get wrapped up in saying, well, should I just spend the money and buy the 6400 encoder count? Discuss that with Teknic, okay? There are 2 different lines of motors. We didn't talk about that. The SDSK and the SDHP. SDSK is fine for most stepper motor applications, okay? Like my machine or a router or plasma cutter, something like that. SDHP, the high performance, is a much higher power motor, and it's meant for larger, heavier, rigid machines that require that power to get them moving or move them quickly to where they need to be. In the type of machine we're talking about here, the SDSK will be just fine. So we just went over the motors, and then the IPC-5 350, 500 watt power supply is in here, and the power cable. So let's get into that. Okay, so this is the power cable for the IPC-5. It's got a standard plug on the end of it, and it gives you instructions on what to do. I'm not going to use a plug. I'll cut the cord and power it up, and I'll be using 240 volts. And it says, attention, how to modify the IPC35 cable 1110 for use with 190 to 250 volts. There's a jumper here that needs to be removed, and we'll go over that when we set things up on the bench. Okay? So let's do the 3411S RLN motor. Wow, that's small. So there's two of these. That's for X and Y. So here is there's the motor, and boy, that thing is much smaller. Oh no, well, when you look at the motor itself, it's much smaller than the stepper motor, and then when you add the drive electronics, it's about the same depth stack as the original, maybe a little bit smaller. But remember, all the smarts, the drive is right here on the motor, and then there's the power supply connector, and there's the data connector, and this is where the molded connectors get plugged in. The tuning port, or the USB port, is right behind this cap, and incidentally there's an LED in there that gives you blink codes. It lets you know when the drive is okay and the motor's ready, or if there are any error codes, it will blink and you'll see it through this cap, so you want to pay attention to that. So that's our 3411S-RLN motor. There's the other 3411S RLN. And here's the little bitty one. This is the NEMA 23 for the 4th axis. It's the CPM SDSK 2321S-RQN. Let's take a look. Oh, that's a little thing there. So there's the small motor, the NEMA 23 motor. It's probably about the same. I can't tell because I'm looking over at the machine, and I can't tell because there's a cover over that stepper. But again, there's the data port, and there's the power supply port on the motor, and it's got the same cover for the USB connector and the LED for blink codes. So this is a bigger box. I'm going to guess this is our Z-axis motor. Pull this out of the way. Yep, there's our Z-axis motor. It is substantially taller, but I'm also looking at the stepper motor, and they're about the same height, so that's good. And you'll recall earlier, that just reminded me, this is another thing. My machine's Y-axis motor is in the back between the cabinet and the column, so you have to be careful. I have to be careful on the depth, but it looks like the new motor is going to fit in there just fine if it's the same. So there's our Z-axis motor. Not putting these back in, all right. Where am I? There we go. Put that back in. So the last box will be the power supply. Yep, there it is. This is the IPC-5 power supply. And let's take a look at this cable. This is the IPC35-cable 110. It has a Molex connector on it, and it plugs in here. So yeah, there's there's that cable, and there's that jumper. And the directions say this jumper wire must be removed and the plug be cut off with properly rated, well, I guess we should just pull it out of the bag, right? We can see this. How to modify the IPC35 cable 110 for use with 190 or 250 volts. So if your machine is set up for 110 volts, you can just leave that jumper, leave this jumper alone. There it is right there. Leave it alone. But if you're going to go with 240, you have to remove it out of the connector socket, or you need to cut it, remove it. That's what it says right here. It says this jumper wire must be removed. See details below. You can use a preferred method. If you have the tool, you can pop the connector out, or you can clip it. And then it says insulate with heat shrink tape. Note exposed leads are a shock hazard. So cap it, tape it, do something so that those are insulated. So this is power to the power supply here. And then the PC Saber SBR 72. Has that Saber connector, and it plugs in to one of these two ports, and then the other end's going to go to that power hub. All right. So that's all our Clearpath stuff. I'm going to go ahead and box this stuff back up so it doesn't get dinged up. There we go. Put that back. And then the last thing to show off, and I'm very optimistic about using this, is the Clearpath C86 ACCP R2-S3620-23. This is the newest revision. And so here's the board, and you can see here's the pins that goes into the Acorn, the 4-axis, X, Y, Z, or axis 1, 2, 3, and 4. And then here are the Molex connectors right here. Interesting, if you have a router, this has already the ability to split out and slave an axis. That's why there are actually 5 connectors here. And then you just move the jumpers here. We won't obviously need to slave it, but they've thought things through and allowed you to hardware pair a slaved axis. So yeah, so we'll be using that. So again, the motor connectors, the Molex connectors will plug on right here. Okay. Oh, the one thing I did fail to mention, these cables, there's nothing proprietary about the connectors. I did mention they're Molex mini fit connectors. So if you have the right tools, you can make up your own connectors. You can crimp them and make them up. Personally, for the money that the cables cost, I just buy the cable and save yourself the grief, because this will plug right into C86 ACCP. And hopefully we're off and running to the races. Okay guys, that's about it. Pretty much all discussed out. We had the unboxing, we discussed Acorn and Clearpath SDSK, we talked about machine mechanics and basic wiring and open loop versus closed loop. So the next time we will do a bench test. We'll set up to do a bench test. We will establish communications with Acorn with a CNC PC and get that going. And then we'll get the C86 ACCP connected to Acorn. And then we'll get a motor set up, we'll get the power hub set up, we get power supplies set up, and we'll try and get a motor turning. All right, until next time, we'll talk to you soon.